So let's check out practice 11.3. And just looking at the first problem here. So I've already written down the function here. And here is the derivative. So s prime. And our input variable here is t. So I'm just using that same notation. The function name is s. The input variable is t. And then here is the limit as h goes to 0, which is the definition of the derivative that we're going to use here. And they're also telling us from the problem that t equals 2. So they are telling us this. And we can use that in the limit, actually, if we wanted to make the work a little bit easier for now, which we can do in 11.3. We won't be able to do this in 11.4, though. So we can right now just plug 2 in for t, because they're telling us that's our point of interest. And this is all they're looking for this first question. And then when it satisfies this is b. So again, just to be clear here, this line right here, let me get this out of the way. This line right here is the derivative. This is the definition. This is where we start. They're telling us that t equals 2, and so just plugging that in. And that is selection B. And they now want us to figure out, so what is the instantaneous velocity at t equals 2? So they want us to figure out exactly what this is here. And actually, I should say something quick in advance. I just noticed with this that they're telling us the position function is this s of t. S of t is the position function. It turns out that the derivative of the position function is velocity. So that's something in physics that they're using here. So they're giving us a position function, and the derivative of position is velocity. So that's why they're asking us here for velocity. That means take the derivative, and that's what we're doing with the limit definition here, is we're going to take the derivative. So in order to do this, we're going to need to know, well, what is s of 2 plus h? And we'll plug that into the original function up here. I know you can't quite see all that together, but I'm just plugging into the top up here. So I just plugged that 2 plus h all into the original function. And we need s of 2. Which again, I'll just plug into the original function here. Oops, made a little error there. It's meant to be a 4 there. So 2 squared plus 4 times 2. Looking up this there. 2 squared plus 4 times 2 plus 2 gives us our s of 2. And this is just a number here we can figure out. So we've got 4 plus 8 plus 2 to give us 14. And let's go ahead and plug that into the limit. So s of 2 plus h is right here. We just figured out. So we're going to plug all that in. And then we subtract off s of 2. And s of 2 we found out to be 14. And that's all divided by h. So let's distribute all of this stuff out and gather like terms. Remember, our goal here is to always get rid of this h in the denominator. So just factoring or distributing out the numerator here. And 2 minus 14 will get us a minus a 12. And let's see what we got here. We have 8 and 4. That's 12. And a minus 12. So those will subtract out. So we're left with 4h and a 4h, which is 8h. I'm actually running out of a little bit of room here. Let me just kind of shortcut this a little bit. So we've got 8h. So 4h plus 4h. And then we have our h squared. And this is all over h. And so we can have an h divide out to get 8 plus h. And then this is our final limit. And what is this forever getting, as h goes to 0, what is this forever getting closer to? It's forever getting closer to 8. And that's our answer. So let's check out the next one. We've got another position function they're giving us, and they're asking for the velocity. So that again means taking the derivative with this new limit that we've learned about. And I'm just going to pause this a moment to write stuff down. All right, so now I got everything written down here. Got the function written down. We're interested in t equals 1. And then here's our derivative definition, this limit. And we're going to solve this problem. So what 13.3 is doing, their first step, is they're taking t equals 1 and they're just plugging it right into the limit. And this isn't wrong. It's not normally done, but it's not wrong. And you'll see in 11.4, the very next section, what we normally do here. Normally we solve this all with the variable and then plug the number in last is what we normally do. But for 13.3, they're plugging the number in first. And the philosophy here, I think, is that people tend to learn easier with numbers versus the letters. So I think that's the philosophy they're going with in 11.3, plugging all the numbers in first. And so that's all I did. All I did was plug in 1 for t. And we get this result for our limit. And this is telling us what we need. We need to figure out then, what is s of 1 plus h? Well, we'll just plug 1 plus h into the original function. And this is also telling us we need s of 1. And we get that, again, by plugging 1 into the original function. And now we actually we can figure out this number here because this is 5, 10, 12. And we take this information and we plug it into the limit. So s of 1 plus h is all this stuff. And then we subtract off s of 1, which we figured out was 12. And that's all divided by h. And so we'll distribute all this stuff out and hope terms cancel. Our ultimate goal is to get rid of this h. So first off, 1 plus h squared is 1 plus 2h plus h squared. And then it has to be multiplied by 5. So that'll give us 5 plus 10h plus 5h squared. And then we'll distribute a 2 into this parentheses here. Get us a 2 plus 2h. And then 5 minus 12 is minus 7, all divided by h. And we'll gather like terms. So 5 and 2 is 7, and 7 minus 7 is 0. So these subtract out, the numbers subtract out. And so what are we left with? We're left with 10h plus 2h. So that's 12h. And we have a 5h squared. All over h. Now, because we can factor an h out of the numerator, means we can now get rid of the h in the denominator, because now these will divide out. And so we're left then with the limit that we have to solve of being 12 plus 5h. So as h gets forever smaller, well, 5 times something that gets forever smaller means this whole thing is getting forever smaller, going to 0. Sometimes this is written with an arrow through it as going to 0. And if this is going to 0, then the limit of this infinite process, the limit of this is 12. It's forever approaching 12. And that's our answer. So let me set up for the next one. All right, so just wanted to write everything down there. So I got the function. Our point of interest is t equals 4. And the definition of the derivative. So, actually, I'm going to do this the normal way. And this is the way you're going to do it in 11.4. And the way that's most commonly done. And what I mean by that, actually I don't need that, is that we're not going to plug in the number first. Usually we plug in the number last. And so let's do that. So what does that mean? Well, that means we need to figure out what is s of t plus h. Not 4 plus h, but t plus h. And that's no big deal. We're just going to plug t plus h into the original function. And then we need to figure out what is s of t. Well, that's already given to us. It's the original function. So we have all our information now to put into the limit. And that's what we'll do. And actually, I'm going to give myself more space on this. So s of t plus h is all this stuff. And now the definition says subtract off the original function. So we're going to subtract off the original function. Now the original function has multiple terms that this minus sign will distribute across. So I'm going to use parentheses here. And that's all divided by h. And so now we're going to distribute all of this out and gather like terms. So first off, t plus h squared is t squared plus 2ht plus h squared. And then we multiply this by 4. Moving on to the next, minus 7, we're going to distribute to t plus h. And then we just have our minus 8. And then we're going to distribute the minus sign to everything in the parentheses here. And this is all divided by h. And now we're going to look for things to cancel. So for instance, 4t squared minus 4t squared. gone. Minus 8 plus 8, gone. Minus 7t plus 7t, gone. And let's look at what's left over. So we've got 8ht remains, plus 8h squared remains, and a minus 7h remains, all over h. And the numerator has a greatest common factor of h, which means we can now divide out the h in the denominator. And we accomplish our goal of getting rid of that h. And so we're left with the limit of 8t plus 8h minus 7. So as h gets forever closer to 0, means this here is getting forever closer to 0. And so what is this forever approaching? As this gets forever closer to 0, this limit is approaching 8t minus 7. And we call this then the derivative. This is the actual derivative function, which is ultimately what we normally want. We normally want the function. Because now that we have the function, we can answer any number question. Now, they, in this case, want us to do t equals 4. So we can just plug 4 into our derivative. To get our answer. All right, so here's the setup for the next question. We got our function, our point of interest, and the definition of the derivative, the limit here. Now, this particular question has t cubed in it. So we're going to have to eventually distribute out a cubed here, which means there's a little bit more work for this one. And because of that extra work, I'm actually just going to plug the number in first. Plugging the number in first does save us some work. However, it doesn't get us the derivative function, which is normally what we desire. So, mathematically speaking, when doing calculus, so I'm just going to plug in the 2 here. And so we want to figure out, well, what is s of 2 plus h? And so we'll plug that into the original function to get that. And we also need s of 2. And so we'll just plug that into the original function to figure out that. And 2 cubed is 8 minus 4 plus 5 gets us a 9. Now what's going to take us a little time is to distribute this one out. And I'm just going to do that now. Let me just distribute this out. It doesn't matter if you distribute this out now or after you plug it in. It doesn't matter. These are choices you can make. These are all choices. You know, there's many choices you can actually make in the order you do things that kind of makes everybody's work more personal to them and their approach towards things. So let's just do that. 2 plus h cubed. Now, how I do this, because I don't memorize the cubed formula, is I first just do 2 plus h, and then times 2 plus h squared to do this result. Because 2 plus h squared is something my brain can quickly process out. And now I can do the distribution of all this to get the cubed answer. So 2 times everything in there. And then h times everything in there. And that gets us our cubed result. So we're going to have 8. I'm going to have to write this all out again. So that's the cubed part. And now we subtract this squared part. So we're going to subtract squaring it. So 2 plus h squared. And then that's plus 5. So this is s plus h. So let's see if we can clean this up. I can't even fit that all on the screen. I suppose if I do it at an angle, maybe. So first off, 5 and 8 is 13 minus 4 to get us at 9. (8h) plus 4h is 12h. Minus 4h is 8h. So I'm doing those. Next in line here, h squared. So 2h squared plus 4h squared is 6h squared. Minus h squared is 5h squared. And then all that's left over then is the plus h cubed. This is s of 3 plus h. So there it is in its simplest form. So plugging this in to the limit. So the first thing we plug in is this. We have 9 plus 8h plus 5h squared plus h cubed. And then we subtract off. So again, I'm going back to the definition. Oops. Just a quick here. I've said 3 plus h here. It's actually 2 plus h. Or, yeah, 2 plus h. So we're looking at 2 plus h, and then we subtract off s of 2, which we figured out was 9. And so we're subtracting off 9 from our answer here. And it's all divided by h. So just to be extra clear here, this is s of 2 plus h minus s of 2 all over h. And if we look at this, we have a minus 9 and a plus 9. And those subtract out. And we're left with these 3 terms here, which all have a factor of h in common. Which means that the h's now divide out, which is exactly what we want. And so what's left over for our limit is 8 plus 5h plus h squared. and h goes to 0. H is going to get forever closer to 0. As h gets forever closer to 0, this will get forever closer to 0. And h squared, which is 0 times 0, this is getting forever closer to 0 as well. And so what is this limit ultimately approaching? It's approaching 8. And that's our answer. All right, so looking at the next one here, got the function they're giving us, the point of interest, and the definition of the derivative. And just to be clear here, instantaneous rate of change is another way of saying the derivative. We want the slope at one particular point, and that particular point being x equals 2. So let's plug 2 in to start with. Because the math is slightly easier if we start with the number, although it's not as powerful. And this tells us what we need to figure out. We need to figure out, well, what is f of 2 plus h? And we get that by just plugging 2 plus h into the original function. And we also need f of 2, which again we get from the original function. And in this case, we have 4 plus 10. And now we'll plug this information into the limit. And subtracting off f of 2, which is 14, all divided by h. And we will distribute all this stuff in the numerator and gather like terms, hoping that we can ultimately cancel this h. So there's distributing everything out, and let's see what we have. 4 plus 10 is 14, minus 14, gone. And that's it. So what's left over here? We have a 4h and a 5h. Take this, a 9h and an h squared. And we do have a common factor of h in the numerator. And now those h's cancel, which is exactly what we want to happen. And then we're left with 9 plus h. And as h gets forever closer to 0, this limit is getting forever closer to 9. And that's our answer. All right, so here's the setup for the final problem here, number 6. G of t, 5 minus t squared. Our point of interest is minus 5. And then here is the derivative definition. And I'm going to start with the less work way, and that is to start with the number. I'm just going to plug the number in for t. Again, this is slightly less work, starting with a number, but it doesn't get us the function that is more valued, which is what we'll do in the next homework. So for this first homework, just plugging the number in first. The next homework, however, we will plug this number in last. So we need to figure out what is g of minus 5 plus h, and we'll get that by just plugging it into the original function. And we also need g of minus 5. Again, from the original function. And we have 5 minus and minus 5 squared is positive 25, but of course there's a minus sign sitting in front of it to get us a minus 20 there. And let's plug this stuff in. And actually, let me do this. Let me distribute this out here as well, just to show you that you can do these steps in whatever order. As long as all your math is consistently logical, it's not going to matter the order you necessarily do things here in. So let's just distribute this out. So minus 5 times minus 5 gives a positive 25. And then minus 5h plus minus 5h is minus 10h. And then h squared. Oops, I really had to squeeze that in there. And then, of course, the minus will distribute to each of these terms. So our first thing to do is plug in g of minus 5 plus h. So that's this first part here. So g of minus 5 plus, so we have 5 minus 25. That's minus 20. Minus a minus 10h is a positive 10h. And then minus h squared. That is g of minus 5 plus h. And then we subtract off g of just minus 5, which we figured out was minus 20 all over h. And we'll clean this up. So we have a minus 20 and a positive 20. Minus minus gets us a positive. So those subtract out, they're gone. And what's left is 10h minus h squared over h. And we now have our factor of h in the numerator, which will divide out with the h in the denominator. So our final limit is 10 minus h. So as h gets forever closer to 0, this is getting forever closer to 10. And that's our answer. And there is practice 11.3.